Hey guys, this is Jack again with another video. In this one, we'll be working on a combustion problem from the Chem 101 homework practice. The problem reads, it's about caffeine. Combustion of 10 grams of caffeine produces 18.13 grams of carbon dioxide, 4.63 grams of H2O, and 2.885 grams of nitrogen. Determine the molar mass of the compound if it is between 150 and 210 grams per mole. So we're going to be going through this problem. It is from the Chem 101 worksheet. So if you want to work through it by yourself beforehand, I'd say pause this video now and come back later, or just stop watching, go try work the problem on your own, and then come to this video if you have any problems. So fair warning. So yeah, let's get her going here in a second. I'm going to switch over to my work screen. Okay, pulling it up, pulling it up now. Here it is. Okay, so I wrote out the problem basics. We have 10 grams of caffeine with excess oxygen at this combustion reaction, which yields these values. Okay, so the first step here is to convert the grams of products into moles of our constituent elements other than oxygen, because that's an excess. And so the first one that I will work through, I'll just do them in order. So 18.13 grams CO2 or 44.01 grams of CO2 in 1 mole of CO2, and 1 mole CO2 has 1 mole of carbon. Calculator. So if I plug this in quickly, that gives me 0.6 figs 4120 moles of carbon. I'll repeat this with the water, or H2O, 4.639 grams H2O. There are 18.02 grams H2O and 1 mole of H2O. And these are just in a similar way to how you learn the elements as you work through. There's like molar masses of certain things that you'll just get used to using a lot. And it's like, I've used water a lot in working problems or in labs. The same thing with CO2. And so those are molar masses I have memorized and that you will get used to learning as you go on. And then continuing on the problem, 1 mole H2O has 2 moles of H, right? 2 H's here. So yeah, and that yields, computer, 4.639 divided by 18.02 times 2.5149 moles hydrogen. And then we have what? 2.885 grams of nitrogen 2. There are 28.02, 0.01 actually. Into 1 mole of N2. And yeah, and 1 mole of N2 is 2 moles of N. And so 2.885 divided by 28.01 times 2 equals 0.2060 moles of nitrogen. Okay, so we can then, so now that we know how many moles of the non-oxygen elements we have, what we can do is we need to discover the moles of oxygen present and the initial caffeine. Is the way to do that is to figure out how much of the initial caffeine was oxygen. And so what we'll do is we will take the moles of these that we just solved for, convert them to grams of the pure element. Note that in the case of the nitrogen, we won't have to because it was pure nitrogen, just in a different form, but all of that mass was still nitrogen molecules or atoms. And so I'm going to take the carbon and convert that to grams down here. Times 12.01. So that gives us about 4.948 grams of carbon. And we'll repeat that with hydrogen. 0.5149 moles of hydrogen. 1 mole of hydrogen weighs 1.01 grams. And so 0.5149 that's 1.01. We have about 0.5200 grams of hydrogen. We know from above that we have 2.885 grams of nitrogen. And so what we can do now is we know that there are only 4 elements in the reaction. We have the carbon, hydrogen, oxygen, and nitrogen, right? So tron. And we know the mass of the carbon, the hydrogen, and the nitrogen. And so by subtracting from the total, right, we take 10.0 grams total. And we subtract 4.948 grams of carbon. We subtract 0.5200 grams of hydrogen. We subtract 2.885 grams of nitrogen. And that should give us our grams of oxygen left. So let me just do this real quick. Yeah, okay, so 10 minus 4.948 minus 0.5200 minus 2.885. That gives us 1.647 grams of oxygen. And if we check significant figures, it is the tens place is the largest shared decimal. And so the significant figures here, it would just be 1.6. However, for the sake of the math, I will be keeping the 1.647, but when we come to the end, it'll just have 2 significant figures. Okay, so knowing that, we can now convert to moles of oxygen. So 1.647 grams of oxygen. There are 16.00 grams of oxygen in a mole of oxygen. So we know that there are 0.10, with this being the significant figure, 3 moles of oxygen present. And then what we'll do is I will just, because the way I like to do my math, bring this down here. So we have all the values next to each other. And then we will divide them all by the lowest value of moles. And so each of these will be divided by the 0.103 moles of oxygen to find a whole number ratio. So yeah, you'll bring that down for all of these. And you will calculate this. So 0.103 divided by 0.103 is 1. Oh, forgot the significance on these. Okay, 0.4120 divided by 0.103 would be 4.5149 divided by 0.103 is 4.999. Yeah, that's 5. I'm just gonna write that as 5. And then 0.2060 divided by 0.103 is 2. So this gives you our empirical formula, right? So we have, let's see, C4, H5, O1, and N2. So this is our empirical formula, but it asks for molecular formula. And so what we'll do now is we will find the molecular weight of this. So it's 4 times 12.01 grams per mole of carbon plus 5 is 1.01 grams per mole hydrogen plus 1 times 16.00 grams per mole oxygen plus 2 times 14.01 grams per mole nitrogen. Adding these up. Plus 5.05, 16. We get 97.11. But if you remember before, the problem asked, or the problem stated that its molar mass is between 150 grams per mole and 210 grams per mole. 97 does not fall in that range, but by switching back real quick, sorry. Okay, and so here it is. By doubling this, right, 97.11 grams per mole. It is not between 150 and 210. No, it doesn't fall between these values. But if we double it, so times 2, we get 194.22 grams per mole, which does fall in that range, which means that we have to double our empirical formula to get the molecular formula. And so in reality, it is this times 2. And so it should be C8H10 O2 N4. So yeah, we'll go back over here. Oh, it just said to determine the molar mass. Awesome. So that's not the answer. This is the answer. My bad. Yes. So in this case, this right here would be your answer. Sometimes it would ask you for what the molecular formula would be rather than the empirical formula, in which case you'd have to go through this and just find what you doubled it, what you multiplied it by, and do the same thing to your empirical formula to get the molecular formula. So yeah, that is the answer. let's plug it in a check. 194.22. Actually, yeah. It won't let me input it. Never mind. Ta-da. I did get it correct. I put an extra significant figure. So this problem wouldn't really actually have significant figures for the molar mass unless we were given specific things here, because all we found here, I'll go back to my screen, were the whole number ratios. And then we used those with, so yeah, all we found were the whole number ratios, which we used to create the empirical formula. And those have no significant figures, right? They are quote unquote infinite. They're exactly 1, exactly 2. You can't have 1.5 carbon atoms in a molecule. And so we just use those along with the information given in the periodic table to come up with it. I decided to use 2 significant figures, but yeah, a problem like this does not have significant figures in the answer other than the ones given by the periodic table, if that makes sense. If you have any other questions about this, leave in the comments. Thank you guys for watching, and I'll see you in the next videos. Bye.